In this particular video, we're going to talk about how to find the longitudinal Young's modulus E1, and this is also going to stand for these particular elastic moduli as well of the unidirectional lamina. So that's why I put down all four there. The first thing which we have to think about is that if we're going to use a strength of materials approach in order to find E1, is that this is the typical unidirectional composite, which will look like this. If you look at its cross section, there'll be several fibers, surrounded by matrix. But what we're going to do is we're going to take a representative volume element, guys. We're going to take a representative volume element right here, and that looks like this. So now you have fiber here and surrounded by the matrix right here. And the representative volume element is taken in such a fashion that the volume fraction of the whole composite and the volume fraction in the representative volume element is preserved, which would make the case for it to be called a representative volume element. Now, one of the things which we have to do is we have to take this circular cross section of fibers and spread it around into a rectangle so that we can apply the strength of materials approach. So which means that the cross section area of the fiber, of the circular fiber, will be same as the cross section area of this particular rectangle right here. Some terminology right here which you are seeing, this is the length of the composite, that's the thickness of the composite, that's the height of the composite. This is the thickness of the fiber, and the thickness of the matrix is distributed on the two sides as such. So if you look at the volume fraction of the fibers, that will be equal to the height of the composite times the thickness of the fiber multiplied by the length of the composite, as you can see. And this is the volume of the composite itself. So you can see that H and H cancels, LC and LC cancels, you get TF by TC. In fact, you get the same as AF by AC, that if you look at the fraction of the areas, you get AF by AC, and you get AM by AC here. So bottom line is that the volume fraction of the fibers is same as the fraction of volume of the fibers, same as the relative thickness of the fibers of the composite, and relative cross-section area of the fiber to the cross-section area of the composite itself. So remember that because that will come in handy when we find the formula for E1. So in order to find E1, what we're going to do is we're going to stretch in the direction of the fibers, which will be just here. So we're going to apply a uniform longitudinal strain on this representative volume element to calculate E1. And let's see what happens there. So what we're seeing right here is that the force in the normal force in the composite will be equal to the normal force in the fiber plus the normal force in the matrix, which makes sense because the force is taken by the matrix and taken by the by the fiber. We also know, we are familiar with these kind of relationships, right? Simple relationships like sigma is P by A and sigma is equal to E epsilon type of things. And that's what we're doing here. We're saying that the normal force in the composite is the normal stress in the composite times the corresponding area. Same thing for the fiber, same thing with the matrix. Normal stress in the composite is equal to E1, which is the Young's modulus in direction 1, times the strain in the composite. And we'll do the same thing for the fiber and the matrix. Now what we're going to do is we're going to plug this in here and then plug the stress relationships right here and see what comes out of it. And this is what we see, that hey, this is the starting relationship, that the normal force in the composite is equal to the normal force in the fiber plus the normal force in the matrix. This is the stress in the composite, this is the corresponding area in the composite, and same thing for the fiber, right? But when you're going to apply a longitudinal strain to this particular composite, you'll find out that hey, the strains experienced by the composite fiber and the matrix will be the same. So this, and this will cancel. Now what we can do is we can divide by AC on both sides. This is what we're going to get, right? Dividing by this AC on both sides. So we'll get E1 on the left side. But we just said that hey, the ratio of the cross-sectional area of the fiber and the matrix is itself the volume fraction of the fiber and the matrix itself. So that gives us the relationship between Young's modulus and the Young's modulus of the fiber and the matrix, and how much of the fiber and how much of the matrix is present in the unidirectional composite. There's another thing which people are interested in, what they want to figure out, that when you are applying this normal stress in the direction parallel to the fiber. So let's suppose you have this composite right here and you're applying some load to it. Let's suppose the load is FC. How much of this load FC is taken by the fibers and how much of it is taken by the matrix? So in order to do that, all we have to do is we repeat these formulas which we had for the stress and the forces. Then if we want to find FF divided by FC, that'll be nothing but sigma F AF divided by sigma C AC, right? And then that will be, what is sigma F? It's EF, epsilon F, AF, and this will be E1, epsilon C, AC. But this and this is going to cancel because the strains will be the same. So we'll get EF by E1 times AF by AC, which is nothing but the volume fraction of the fibers right there. So that is the formula for how much of the load is taken by the fibers to that of the composite itself. So what we have done in this case here is that we have plotted how much of the load is taken by the fiber to the composite load as a function of the fiber to matrix moduli ratio, that is the EF by EM, for different fiber volume fractions. So let's look at it specifically rather than trying to figure out what's going on here. Let's look at glass epoxy. The glass epoxy fiber to matrix ratios are around 20 or so. And you can see that already, even for small volume fractions of 20%, 80% of the load is taken by the fibers. And as you can imagine that as you increase the fiber volume fraction, right, more and more load will be taken by the fiber because there's more of the fiber there. So both of those things, you have to understand that if the fiber to matrix moduli ratio is high, then more of the load is going to be taken by the fiber. If the volume fraction of the fibers is high, then more of that load is going to be taken by the fibers itself. And the formula which we just derived is right here. Let's go and take an example. So we want to find the longitudinal elastic modulus or longitudinal Young's modulus of a unidirectional glass epoxy lamina. The properties are given in table 3.1 and 2. It is 70% fiber volume fraction. EF is given as 85 gigapascals, EM is 3.4 gigapascals. So we derived just this formula just now. So all you do is 85, 3.4, 70% is 0.7 fiber volume fraction. And that corresponds to the fiber volume fraction corresponding to the matrix will be 0.3, and that's what we get here, 60.52 GPa. Let's look at how much is the force in the fiber to the composite ratio. And 85 gigapascals is the Young's modulus of the fiber. 60.52 is the Young's modulus of the in the direction parallel to the fiber, which we just found out. 0.7 is the fiber volume fraction, and saying it's 0.9831. So what you're basically seeing here is that more than 98% of the load is taken by the fiber itself when you are applying a uniaxial load on a 0-degree ply or a unidirectional ply. We wanted to see that how good our formula for E1 is, which was EF VF plus EM VM, right? And we want to see how good this formula is, and you're finding out the experimental data points are very close to your fiber volume fraction, to your straight line approximation of the Young's modulus E1 right here. So that's a good sign that even a simple formula like this one is giving us good results when compared to experimental results. And that's the end of this segment.